Welcome to today's paper reading. Today's paper is titled, A Comparison of Human, GPT-3.5 and GPT-4 Performance in a University-Level Coding Course. This paper was published on the AR14 preprint by Yeadon and colleagues from Durham University. This study examines the performance of ChatGPT variants, GPT-3.5 and GPT-4, in university-level physics coding assignments using Python. The research compares 50 student submissions to 50 AI-generated submissions, marked blindly by 3 independent markers, resulting in 300 data points. Students averaged 91.9% with a standard error of 0.4, outperforming the highest AI category, GPT-4 with prompt engineering, which scored 81.1% with a standard error of 0.8. Prompt engineering significantly improved scores for both GPT-4 and GPT-3.5. Additionally, blind markers accurately identified authorship, with 92.1% of definitely human submissions being human-authored. Simplified to a binary categorization, the average accuracy rate was 85.3%. These results indicate that while AI-generated work closely matches student quality, it is often detectable by human evaluators. Coding courses are now a standard part of university curricula worldwide, reflecting the growing importance of programming skills in the digital economy. The advent of advanced large language models, LLMs, such as Codex, which powers GitHub Copilot, necessitates a reevaluation of the effectiveness and integrity of coding assessments in educational settings. While LLMs have been tested on coding abilities through benchmarks like MBPP and MathQA Python, this study examines AI's potential effects on university coding courses. Unlike previous work that evaluated AI's capacity to solve coding puzzles, this research investigates AI's impact on a practical coding curriculum. Specifically, we focus on a 10-week coding course within a physics degree at Durham University, where students engage in lectures and complete assignments on an NB-Grader-powered Jupyter Notebook server. Physics degrees offer a diverse range of assessments, from lab-based experiments and presentations to written exams and coding assignments. This variety provides a unique opportunity to assess AI's impact on various forms of academic assessment. The study aims to determine the ongoing validity, utility, and integrity of coding assignments and accurately assessing student performance in an era of rapid technological development. The study aims to evaluate the effectiveness of large language models, LLMs, in performing coding tasks traditionally assigned to university students. This is done through a blinded marking approach to compare code written by students and AI. The context of the study is physics, where coding is used for simulations and data analysis, with a focus on plot quality and code runtime. The coding assignments used in this study are from the Laboratory Skills and Electronics module at Durham University, which spans 10 weeks and includes 8 weekly assignments. To simulate AI completion of these assignments, the notebooks were preprocessed to align with AI processing capabilities. This involved completing graded cells, excluding assert statements, and converting tables into Python dictionaries. Additionally, prompt engineering was used to enhance the interaction with the LLMs, resulting in 5 categories of AI-generated work: GPT-3.5 raw, GPT-3.5 with prompt engineering, GPT-4 raw, GPT-4 with prompt engineering, and mixed. Each category produced 10 submissions, totaling 50 AI submissions, which were blindly evaluated alongside 50 student submissions. Table 1 outlines the necessary preprocessing changes applied to raw.ipython files to convert them into Python scripts suitable for completion by large language models, LLMs. These changes are crucial for ensuring a fair comparison between AI-generated and student-generated submissions. The first key point indicates that 30 to 60% of the marks, which are tested via assert statements up to the plotting tasks, were completed with correct answers. This ensures that the AI focuses on the relevant parts of the assignment. The second key point highlights the use of the text here to direct the AI to the specific location for code input, ensuring consistent responses. Lastly, the exclusion of assert statements for autograding is noted, as these are not relevant for the AI or students and are only pertinent for behind-the-scenes operation. Table 2 outlines the specific steps taken in prompt engineering to optimize interactions with GPT-3.5 and GPT-4 models for coding assignments. The first step involves rewriting function definitions within notebooks for greater clarity. The second step removes any non-task related information to focus solely on the assignment requirements. The third step adds an enhanced preamble to clearly outline the task and instructions, including marking explicit locations for code insertion. The final step elaborates on post-task details to further guide the completion process, specifying objectives and offering suggestions to enhance plot clarity and effectiveness. In the score comparison, students achieved an average score of 91.1%, while GPT-4 with prompt engineering scored 81.1%. A t-test revealed a significant difference with a t-statistic of -8.193 and a p-value of 2.482 times 10 to the power of -10, indicating that GPT-4, while capable, is not as proficient as students in physics coding assignments. Prompt engineering significantly improved AI scores. GPT-4's scores increased from 71.9% to 81.1% with a p-value of 1.661 times 10 to the power of -4, and GPT-3.5 scores improved from 30.9% to 48.8% with a p-value of 4.967 times 10 to the power of -9. This confirms the benefits of prompt engineering. In author identification, using the Likert scale, genuine student submissions were more often recognized as human-authored. A Cochrane-Armitage test showed a p-value of 0.025 and a trend of 0.302, indicating an increase in human-authored submissions as we move from definitely AI to definitely human. Reviewers achieved an average accuracy rate of 85.3% in distinguishing AI from human-authored content. Figure 1 presents the percentage scores for 6 categories of submissions, highlighting that student submissions achieve the highest scores at 91.1%. GPT-4 with prompt engineering closely follows with an 81.1% score, while GPT-3.5 performs notably worse. This data underscores the proficiency of students in coding tasks compared to AI models, even when AI models are enhanced with prompt engineering. Figure 2 presents a histogram illustrating the markers assigned authorship versus the actual authorship of 300 assessed submissions. The data reveals that 92.1% of the code categorized as definitely human was indeed human-authored. This percentage decreases to 73.1% for probably human, 22.4% for probably AI, and 8.4% for definitely AI. This distribution highlights the accuracy of markers in distinguishing between human and AI-generated content. The findings of this study suggest that, in the short term, the most sophisticated AI models might not rival human expertise in university-level physics coding assignments. However, the research highlights a distinct improvement of GPT-4 over GPT-3.5, showcasing the steady advancement of AI capabilities. This evolution suggests that AI's potential to match or surpass human performance is increasingly plausible. Given this trajectory, educators should reassess the role of coding assignments and the objectives of their educational strategies. The integration of AI into educational practices, akin to a pair programming setup, should not be viewed negatively. This approach offers an exciting opportunity for innovation in physics education. From an academic integrity perspective, students are likely to achieve better results by completing assignments themselves. The extensive prompt engineering for AI categories necessitates engagement with course materials, introducing ambiguity regarding academic integrity. Implementing barriers that make pre-processing more demanding than the assignments themselves could be a potential remedy. The study concludes that while the latest large language models, LLMs, have not yet surpassed human proficiency in physics coding assignments, there is a clear superiority of GPT-4 over GPT-3.5. The research also highlights that prompt engineering can significantly enhance the performance of these models. If the improvement trajectory from GPT-3.5 to GPT-4 continues, LLMs may soon outperform student capabilities. Additionally, the analysis revealed that plots generated by LLMs are distinguishable from those created by students due to their misaligned or skewed layouts and default color schemes. In contrast, student plots often exhibit more unique, albeit sometimes garish, design choices. This distinction emphasizes the potential for human markers to identify AI-generated content. The study underscores the importance of considering the degree of human intervention in evaluating the effectiveness of any LLM. Moving forward, these findings suggest a need to reevaluate how we measure AI performance and the role of human collaboration in fully harnessing AI's potential. Thank you for watching.